Alright, this is the Unit 2 exam key. Jumping right into problem 1. An uncharged 5 microfarad capacitor and a resistor are connected in series to a 12-volt battery and an open switch to form an RC circuit. The switch is closed at t equals 0 seconds. The time constant of the circuit is 4 seconds. Determine the value of the resistance. Well, this one is a simple write-down. This is the time constant is equal to the resistance times the capacitance. So the resistance then is equal to tau over C, equal to 4 seconds over 5 times 10 to the negative 6 farads, which equals 8 times 10 to the 5th ohms. Wait, determine the maximum charge of the capacitor. That, again, just simple write down. The maximum charge on the capacitor is given as Q equals CV. We have C is equal to 5.0 times 10 to the negative 6 farads times 12 volts, which is given here. So the charge is just equal to 6 times 10 to the negative 5 coulombs. And the last part says, what is the charge on either plate after one time constant has elapsed? Okay, well that charge is given by Q equals Q naught times 1 minus e to the negative t over RC. At this point, t is equal to one time constant, so RC, so I can just plug that in here. So Q is equal to Q naught times 1 minus e to the negative 1. Or Q from up here, 6 times 10 to the negative 5th coulombs times 1 minus e to the negative 1, and these are just constants here in the bracket. So Q is equal to 3.79 times 10 to the negative 5th coulombs. Okay, question 4. A proton traveling due west in a region that contains only a magnetic field experiences a vertically upward force. What is the direction of the magnetic field? Okay, so if we have north is in this direction, so east, south, west. So the particle is traveling due west. It's a proton, due west. Has a magnetic field and experiences a vertically upward force. So upward must be out of the page. So right-hand rule. Zoom out. So the particle is moving in this direction. The force is up in the direction of my thumb, so the magnetic field must be downward. Velocity, field, force goes in the direction of my thumb. And this is velocity. So V, B, force. Alright, an electron is, I'm going to underline electron. It's a negative charge, negative Q. Actually, I should say negative E. Travels horizontally, enters a region where a uniform magnetic field is directed into the plane of the paper shown. Describe and sketch the trajectory of the electron after it enters the field. Okay, so velocity, field, force is up, but it's an electron, so it's going to be the opposite. So velocity, field, force, but it's the opposite because it's negative. So the force at this instant that enters the field will be downward. But the trajectory is going to be a circle because at each point the direction of the force is going to change. So that's very different than the electric force. Okay, this one is a bit of a tough one. You have 4 wires traveling, vertical like this in three of them, the current is traveling out of the page, and in this one, the current is traveling into the page. So we want to find what the field from each one of those is, and we want to find the field at point P. So then, let's label these 1, 2, 3, 4. The field from this wire is going to be in this direction. The field from this wire is going to, and that's because I point my finger in and I point my thumb in the direction of the current and wrap my fingers in the direction of the field. So the field is going to circle around the wire, and if I just extend this out to this, it's going to be a bigger circle. And at point P, it's going to point in that direction, towards the diagonal. With point 2, it's going to be the exact same thing. There's going to be the circular field around the wire 2, so E2 will be in that direction. For wire 3, it's different though, because now the current is downward, so the electric field is going to circle in this direction, so it will also be in the direction of E1, so I'll put E3 there. For point 4, that's going to be in going out of the page, so my fingers curl around, circular field goes in this direction, which means at point P, E4 is in that direction. So to draw this all again, sum it all up, this is point P, you have E2, you have E4, and then you have E1, E3. Well, the current in all of these wires is the same. I4 equals I2, so that means E4 must equal E2, and these two are in opposite directions, so they add to 0. And that's true because of the geometry involved. So the sum of the magnetic fields is equal to B1 plus B2 plus B3 plus B4, but we can say then that the sum of, well, B4 plus B2 equals 0, because they are the same. Or I could say the magnitude of B4, and just label it without the vector, minus the magnitude of B2, because it's in the opposite direction, equals 0. Okay, so that means the sum of the fields then, if I want to just take the magnitude of it, now I'll put it over here. Sum of the fields then is B1 plus B3. And we know the equation of the magnetic field for a current carrying wire is mu naught I1 over 2 pi R1 plus mu naught I3 over 2 pi R3. Well, I1 equals I3, so we can pull I out of all of that. Mu naught, I'll just call it I, over 2 pi times 1 over R1 plus 1 over R3. Well, R1 equals R3, which is just the distance between the point and the wire. So the sum of the magnetic fields is equal to mu naught I over 2 pi 1 over R. So what is R? Well, if I call this A, R equals square root of A squared plus A squared, where that's just Pythagorean theorem, find the length of between, one wire, from one wire to the other along the diagonal. And it's going to be half that, because it's only half that distance. So this is equal to square root of 2 over 2A, when you simplify. Or you can say R is equal to A over square root 2. Either way is fine. So this can go in here. Oops. So the magnetic field is mu naught I over 2 pi times 1 over R, which is square root of 2 over A. And then when you plug all that stuff in, sum of the magnetic field is 2.3 times 10 to the negative 4th Tesla. Oh, I'm sorry, the 2 should have canceled that from here. So this is our answer. Okay, this next one says we have a loop and a magnetic field. We have the area. Let's see, the induced EMF is 1.2 volts. B final, we don't know what B initial is, but we know B final is 0.30 Tesla, and the change in time is 0.087 seconds. Okay, so this is asking us, the magnetic field decreases to 0.3 Tesla in this amount of time, and that results in an induced EMF of 1.2 volts. So it's asking what is the initial value of the magnetic field, because that's going to determine the induced voltage. So this is an application of Faraday's law, given right here, N times change in magnetic flux over change in time. And this is equal to negative N times the change in the product of BA cosine phi. I should have put down here cosine phi is 0 degrees. Or I'm sorry, phi is 0 degrees over change in T. And I can make that capital A. So the area of the loop is not changing, the angle is not changing, only B is changing, so I'll pull those out. Negative equals negative N B, N A cosine theta, phi. Change in magnetic field over change in time. I can expand this as well. B final, times B final minus B initial, because the delta is B is final minus initial, over change T. Okay, so we have this, we have the area, we have the induced voltage, we have the change in time, we have the final magnetic field, we don't have the original. We know cosine of 0 is 1. So EMF times change in time over negative N, I should say N equals 1 because there's only one loop. A equals BF minus B naught. So B naught is equal to BF minus, let's see. Well, this is already negative, so that's going to be, well, I'll just leave it as delta T over negative NA. These two cancel each other out, so B naught is equal to BF plus the EMF times change in time over NA. And you can plug in the numbers, but it comes out to be 1.9 Tesla. Oops. Okay, you have a conducting circular loop with some resistance. It's a uniform magnetic field and has a certain radius. The magnetic field is directed out. The paper is shown. if the magnetic field is held constant at 3 Tesla and the loop is pulled out of the region that contains the field in 0.2 seconds, what is the average induced EMF in the loop? So the starting magnetic field is 3.0 Tesla, and at the final, the magnetic field is not changing. That contains the field change in time is 0.2 seconds. And radius equals 0.024 meters. So looking at, find induced EMF. So looking at Faraday's law, that is equal to negative N, let's say N equals 1, times change in magnetic flux over change in time equals negative N, and the area is what is changing, so that's also phi is 0 degrees. So is B cosine phi times change in area over change in time. This is area through which the magnetic field is passing. Cosine phi is 1. N is 1. So the induced EMF is negative B over delta T times A final minus A initial. A final is 0. I should have wrote that down, because at that point it's completely out. The loop has been pulled out of the magnetic field. So this is equal to B A naught over delta T, which is equal to B times pi R squared over delta T. Plug in the numbers and you get the EMF is 0.027 volts. So the next question asks the exact same scenario, but it says what is, in that case, what is the energy dissipated in the resistor R? Well, power is equal to IV. If we solve for the current, well, current is V over R, so that means this is now V squared over R, which equals, remember, voltage and EMF is essentially the same thing, EMF over R. So power is equal to 0.027 volts squared over 1.5 ohms. The power is equal to 4.9 times 10 to the negative 4th watts. So a long straight wire is in the same plane as a wooden I should have taken wooden out. I'm sorry. As a conducting loop. The wire carries an increasing current in the direction shown in the figure. Determine whether or not the current will be induced in the loop, and if so, what direction will the current travel? Well, it contains an increasing current. Alright, so if that's the case, the magnetic field, you point in the direction of the current. The magnetic field then is into the page, and it's increasing. So that means the induced field must be out of the page. It must combat that increase. So we need to induce and make a current that will induce a field in that direction. If I point my fingers in the direction of the current and point my thumb in the direction of the current and point my fingers in the direction of the field, which is upward, in the first branch, it's going to go this way, then it's going to circle up, then it's going to come back the other way. That means the induced current will go like this. It will be counterclockwise. And finally, two conducting loops carry equal currents in the same direction as shown in the figure. If the current in the upper loop suddenly drops to 0, what will happen in the current to the lower loop according to Lenz's law? Well, the current in the upper loop is creating a field that is in this direction, and that field extends into the lower loop as well. So if the current in the upper loop suddenly drops to 0, well, then this current must increase to try to keep that from happening. So it must travel in the same direction but increase. And so that is